Hello, everyone. Amelia Thompson here, your host of the Wurth Electronic Webinars, and thank you for joining us for our final Wurth Electronic Power Webinar of 2021. Today's presentation is Meeting the Power and Magnetic Design Challenges of Ultra-Thin, High-Power Density 48-Volt DC-to-DC Converters, powered by Digikey Electronics, the exclusive sponsor of all Wurth Electronic Webinars. Today's Power Webinar is presented jointly with speakers from Wurth Electronic and Efficient Power Conversion. Our first presenter is Brian Miller, Field Applications Engineer with Efficient Power Conversion, followed by Quentin Ledebier, Team Leader for Product Definition Engineering at Wurth Electronic in the Americas. If you have any questions during today's webinar, feel free to ask them in the questions box, and our presenters will answer them at the end. If we don't get to your question, or you think of it a little bit later, simply reply to our email. That's hereforyou@we-online.com. Here, the number 4, YOU, at we-online.com. Now, because you registered for today's event, you will automatically receive the recorded video on demand and a PDF of the slides following the presentation. We'll be back next year with more webinars, but until then, make sure you listen to that new Wurth Electronic What's Up podcast, where each week we are bringing application notes, blogs, webinars, and even our press releases to an audio format. The Wurth Electronic What's Up podcast can be found on all major streaming networks, including Spotify, Google Podcasts, iTunes, and so much more. Now let's begin today's Power Webinar with Wurth Electronic and Efficient Power Conversion, meeting the power and magnetic design challenges of ultra-thin, high-power density 48-volt DC-to-DC converter.
Thank you, Amelia, and welcome everybody to the webinar. First of all, as a way of introduction, there's a requirement in a lot of equipment, both consumer and also other equipment, for thinner and more power. Here's some examples. For example, a thin TV, a thin notebook, some portable equipment, monitors and so forth, thinner and more power for bigger screens and for more processing. Now, how to deal with that? For thin solutions, there's a few different topologies that can be used and be considered. One is synchronous buck converter, which I'm sure everybody is very familiar with, just a half bridge with an inductor on the output. That's one option. Another option is multi-phase converter, where you'd have multiple of these buck converters kind of put together, where each of the phases would be smaller. So that's another choice. Here's one of the phases. It's kind of shown in detail right here, and each one of these blocks is the same. Another way is to have a hybrid synchronous buck converter, where you have more switches and you have just one output inductor, but that can also help lower the size. Switch capacitor converter, you notice on this one, there is no inductor. However, one of the problems here is a fixed ratio sometimes is not very conducive to the final result. And finally, one that got the most attention from all of us and seemed like a very good fit to the problem we were facing is a flying capacitor multi-level converter. It looks very similar to the hybrid synchronous buck converter, but we'll go through some differences in the operation of this converter. First, here's a comparison. The buck converter and the 3-level buck. So the blue, you can see here, the blue is a traditional buck converter, the half bridge. The red is a 3-level buck converter. Now, what does this mean? Up here, this is normalized inductance. So the higher the line, the greater the value inductor that's needed for this particular converter. And the larger the inductor, of course, the larger the whole power supply and the more problems making it thin. So the green bar here is the requirements of the power supply that we're looking at. Inside this block, you can see the blue is very high. The red is very low, so that's very attractive. A lower value of inductor would lead to a smaller size of inductor. Okay, the question is, now that we've determined the topology of a multi-level buck converter, why EGAN FETs? Here's a little comparison chart. First comes the EGAN FET, and then there's two examples of silicon MOSFET FETs. They're all roughly the same voltage, kind of in the same neighborhood of resistance, but then things really start to diverge. Looking down here at the output charge, you can see that the GaN FET is a fraction, looks like roughly a half of that. Also for the GaN FET, there's no reverse recovery loss. The area is smaller, and there's a few figures of merit here. And it's really quite interesting here for the figure of merit for the gate. It's roughly 1/6 or less than the silicon MOSFETs. That's very good. The output capacitance is roughly half, and the figure of merit for the area, so it's smaller. And here's some of the ones highlighted. Gate charge. The dead time loss, again, that's the reverse recovery. So that's basically 0 here. So you don't have to really worry about a dead time adaptation of dead time with the GaN FETs. The output capacitance and the figure of merit for the area. Here's the converter specifications we were looking at. An input voltage of 40 volts to 60 volts, an output voltage of 20 volts, and output current of 12.5 amps, which equates to roughly 250 watts. So it's a 250 watt converter, and the goal is to have it very thin. Let's look at the operating principle of a 3-level converter. This is with a duty cycle of less than 50%, which is what we're seeing here. We'll go down here. First, Q1, the top FET. Second is Q2, which is second FET. And you see the switching cycles here. And Q4, which is the bottom FET. Then we'll put in Q3, which is right down here. And you can see kind of like an interleaving right here. So you add these together and you see the switching waveform alternates between the outer FETs, the Q1, Q4, and the inner FETs. In other words, the middle FETs, Q2 and Q3. What that does is it basically doubles the frequency seen by the inductor as seen by any particular FET, which helps to reduce the need for a larger inductor, also helps the inductor current be a smaller amplitude. Here's an illustration of that, going through the different steps. Notice the current ripple is, like I mentioned, at 2 times the switching frequency. Okay, how to implement this? So you have 4 FETs here. How would you do that? There's various choices of the GaN FETs and different various voltages. Q1's likely to see the input voltage, especially during startup. So the maximum is 60 volts, so it's probably good to use a 100-volt FET in this position. It just is able to withstand the full voltage. Now the other FETs, once it gets working, they will see, including Q1 after it gets started, but for the initial startup. But for the other ones, roughly half, so roughly 30 volts. So there are some 40-volt FETs, which are a very good match. Those are the rest, except the very top FET. You notice it's roughly the same resistance, but a bit smaller due to the voltage. The overall switching frequency is 400 kilohertz, but the inductor sees twice that, 800 kilohertz frequency. That helps to have an inductor, but still the challenges are really there. The challenges are for a very short inductor, 4.1 millimeters tall and 2.4 microhenries. And again, that's for a 250 watt converter, so that's quite a challenge. And to hear more, I'll pass it off to Quentin of Wurth to talk more about the actual design of the inductor.
All right, thank you, Brian, for the introduction. Hello everyone, my name is Quentin. I am product definition engineer here at Wurth Elektronik, working with IC manufacturers and trying to come up with products to fit their designs. So today we're talking about an off-the-shelf inductor design process, particularly using the case study of this inductor that we built with EPC. And let's see what we did for this particular part. So what we're going to see today is the material selection, the core shape, wire selection, the simulation, and some EMI consideration that we had for this particular part design. If you're already experienced in magnetic design, you might find this presentation kind of simplistic and too easy. There are a lot of things that you can do and consider when you design magnetics, but this is intended to be an introduction presentation where we explain the general principles of designing inductors. So yeah, just bear with us for this presentation and you might find actually interesting information. So first thing to consider are the initial requirements that we receive from EPC. Typically we saw they wanted an inductance value from 1.5 microhenry to 3.2 microhenry, a thickness of about 4.1 maximum or 3.5 maximum. This has changed a couple times. We have an average current of 12.5, as Brian said, a peak current of 15 amp, and a frequency that's from 800 kilohertz to 1 megahertz. This is a pretty high frequency for that power level, so that was one of the main things to consider in this design. And another big thing, a big factor for this design was the working temperature that should be around 40 Kelvin without any airflow to cool down the design. So with all of that in mind, that's when we start to do the selection of a part, and we start always with a material selection. So the first step, the first thing to consider is the type of material. So we can go basically two routes. We can go molded iron powder kind of material, and we can go with a fixed ferrite based material. It could be manganese zinc, could be nickel zinc. And both of them have advantages and inconvenience, but mainly what we are looking at here is the type of saturation that they offer. Well, typically molded iron powder or have a soft saturation, and fixed air gap ferrite have a harder saturation. And oops, let me come back. And that's how you basically do the distinction between them. Now also iron powder typically work better at lower frequency, and fixed ferrites work typically better at higher frequency. So already then we kind of knew that we wanted to go with a ferrite material. So the material that we ended up selecting is a manganese zinc alloy. You can see here on the right a snapshot of all the properties that we have from the manufacturer, the core manufacturer. We're going to go through the main ones and not all of them. So one of the main ones is the saturation magnetic flux. It describes basically how much magnetic flux you can put through this core before saturation. Based on the inductance that you need and on the frequency, you can tailor this part. Now another parameter that you want to consider is the power loss density, and this is helpful to do a quick estimation of how much losses this core will have at the frequency of test, which is in this case 1 megahertz. So it's not a very accurate estimation of the losses of the core, but it's a first step to kind of figure out what the losses are going to look like in this particular core. And from this manufacturer, you can also compare material together because they measure it the same way. But obviously, if your application is switching at a different frequency, then this is not very, very helpful for you, but it could be just interesting. The next parameters to consider are the permeability. Permeability is obviously one of the main factors of the material selection. This is what links the magnetic field with magnetic flux. So it describes how the material behaves when you put a magnetic field through it and how it saturates over a magnetic field. So magnetic field being linked directly with a current, it describes how the core behaves as you put more current through the inductor. So as you can see in this formula above, permeability, variety of permeability of the material is influencing directly the inductance value because it's right there at the top, but it's also in the effective length of the core. So the effective length of a core is the average path of the magnetic field in this material. But when you add an air gap, then the effective length becomes the length of the core plus the relative permeability times the air gap. So in this scenario, which is what most modern inductor have, like an air gap, you always, the permeability is influencing the inductance in two different ways, so you have to be aware of that and select carefully. And then the last thing is the thermal profile. So as you can see on this graph, there are two different curves, one at 25 degree and one at 100 degree. And yeah, it just shows that depending of how you're planning to run the inductor, is it going to be hot, is it not going to be hot, the saturation, the maximum saturation is going to change, and the saturation profile is going to change as well. Now for the core shape. So since we decided to go with the ferrite, what we're trying to do is mostly to stay with standard cores. And the reason for that is simply facility. It's a bit easier to go with standard cores. It's also a lot cheaper to go with standard cores versus going with custom cores. And for that particular design, we decided to go with kind of a EI combination here. So an E core basically as at the bottom, and then a I plate, like just a simple material plate to close this design. So this core shape was allowing us to match to reach that thickness that EPC was looking for, and still be able to expand on the X and Y axis to reach the other properties, the inductance, the rated current, and saturation current. So another thing that you can consider when selecting the core shape is again what kind of air gap am I going to have in my part. For this particular part, for the part that we selected, there was a center air gap which behaves pretty much like this graph on the left here. So that's not the most optimized air gap because obviously you're going to concentrate all of the energy into this one specific spot, this one specific air gap. So it's probably not the best from a loss optimization, but what you can do is also distribute the air gap between the different spots of the design. So you can have a small air gap into the center pin, but you can also have air gaps on the outside pins or on the outside areas here. It's just a little bit harder than to control the coplanarity of the core from the top core to the bottom core. So something to keep in mind, but you would improve your overall efficiency and reduce the heat spots in your part. And then you have the distributed air gap solution, typically for the iron powder molded parts. So when you have magnetic particles that are glued together with binders, basically the glue, the binder here, is creating space between the magnetic particles, and this is the air gap of the part. So it's not like a physical air gap that is cut out or that is well dimensioned, let's say. It's more of a distributed air gap that's within the core. So it's kind of invisible to the naked eye, but it's there. And those will distribute the loss very well and reduce the losses induced by the air gap itself. And typically the difference will be to have two different saturation types. So for instance, those two parts are about 5.7 microhenry at when zero current is going through them. But as you put more current through them and as you saturate them, you can see the difference in behavior. Like the green curve is typically a fixed air gap, like the one we saw on the left here. And you can see that it saturates sharply, and you don't have much margin here. But you can see the blue curve is typically a distributed air gap behavior, so it starts to saturate maybe a little bit earlier, but you can put a lot more current through it, and it will saturate with a kind slope and not too sharply. Now, the last thing that we need to consider, and that's very specific to this case, is the Basin effect that could happen during the production process of a specific core. Our part was about 25 by 20 X and Y dimension, but still very, very thin, around 3.5, 4 millimeter. So what can happen in those scenarios is that, as you can see on this schematic, on this graph here, you can see that it might happen that the coplanarity of this particular face here is not respected. Therefore, it's pushing the center pin a little bit closer to the top plate, and thus changing the air gap dimension. So instead of having the nice air gap that you designed and that you intended, you end up with a much smaller air gap, and then it changes obviously your inductance value, your saturation properties. So that's just something that we had to be aware of, and we knew from past experience with this type of course. So we had to look into that and make sure that we're able to control this Basin effect at the production process. Wire selection. So wire selection is mainly driven by the window area of that particular core that we selected and the number of turns that we need based on the material that we have selected and the core shape that we have selected. So typically you have three main wires: round wire, flat wire, and Litz wire, and they all have advantages and inconvenience. Round wire would typically be easier to do more turns with, and also is very cheap. Flat wire, it's a lot harder to do many turns, but it has a bigger area, thus reducing the RDC. And the Litz wire is very good at reducing the skin effect. We'll talk about this in a little bit, but it's also more expensive, and also takes a little bit more space than the round wire. Number of turns is very critical to control the inductance value, because as you can see in this formula, the number of turns is square, and so it's going to have a big influence into for the inductance value. For our case, as you can see on this graph here, the window area is better used with a flat winding, simply because, first of all, with the inductance value that we go for, and the size and dimension of the core that we selected and type of core that we selected, we don't need to do that many turns. So we only need to do 2-3 turns to achieve the inductance value. So it's not really interesting for us to use a round wire or Litz wire, because it's better to use a bigger flat wire and try to reduce the RDC as much as possible to achieve the best efficiency overall, versus using round wire or Litz wire, which would not fill out the area as well, and also reduce our efficiency overall. So another effect that we had to consider is called the skin death or skin effect. So typically when we put alternative current into a wire, the current tends to flow on the outer skin of that wire. And you can see here how it does. So if I'm switching at 0.1 kilohertz, I'm basically using the whole surface area of my round wire. But as I'm increasing the frequency, then my current tend to concentrate on the outside. So it's not as neat as this in real life. It's like a gradient of current, obviously, but that's kind of the idea. And you can see that because this current is concentrating on the outer skin, then the alternative RDC is increasing in the conductor. You can see the formula over there. And so basically here, just to put that in perspective, I've calculated, I've calculated the surface area of each of these wires. So those are all the same surface area overall, 10 millimeters square. And then I've calculated the outer skin, the perimeter of those different shapes. And so you can see the perimeter of a round wire, 11.2, of flat wire, which is in this case 22, and of the Litz wire, which is 52. So now you'll think, well, obviously the Litz wire is the best. Why didn't you use this? Well, because as I said before, we don't need to do that many turns. So the Litz wire, not so interesting. And also because the Litz wire comes with a downside, is that if you switch at too high frequency, you start to have parasitic capacitance within the windings inside of this winding here. So there is a downside to using lit wire as well, and lit wire, it's fairly expensive, so you don't want to use it too much if you can avoid it. So overall, the flat wire was a very good compromise. So once we have the material, the core, and the winding, we basically have our shape, we know what we want, and that's when we start to go and do some simulations. So to do the simulations, there are some prerequisites that are very actually hard to get together. And the first thing that we need to have is the material information, the material database. And this is critical because the material manufacturers, the core manufacturers, they won't give you a very consistent or good enough sometimes information for our test. So we have to obtain those materials ourselves and do the measurement in our lab in Germany to be able to have consistent results and also as close as possible to reality results for our tests and our simulations. So that's what we had to do for this specific part because we didn't have this material already tested, so we had to get the material from the manufacturer, test it, have it into our material database, and then we can start doing the test. So the stats, what are they? Typically, we can test many things, inductance value, saturation behavior, VH field plot, AD losses, frequency behavior, call losses, S parameters, etc., etc. We can do a lot of tests. What we did for this particular design was the inductance value, saturation behavior, and also we checked the thermal heating of the core and the surrounding, because those were the most interesting ones. And with simulation, you always have this balance of how many tests are you doing and what makes sense, because a simulation takes time and resource. So you want to be straight to the point when you do simulation. So after many tests, we did a few iteration of this design using simulation, try to optimize a few things. But after a while, we had a very good, let's say, initial result, and we ordered some prototypes, and then we were able to compare the simulation result with our prototype measurements. And as you can see, they were very, very, very close. So we're super happy with that because it means that our simulation is reliable, and at least on this type of part, because obviously it changes depending on the part you're building. But for this specific part, it was very, very close. You can see that there is kind of a difference in how it saturates, and that's because sometimes the simulation is not as accurate in reproducing the small parasitic effects in the parts. So sometimes you have some inaccuracy, but overall it's an excellent first step. Last thing that we had to consider for this specific design, and that's just based on experience from us, but this specific part was not too affected by it. There is something to consider when you place an inductor on the PCB, is to always look at the start of winding and make sure that you connect the start of winding to the switch node or to the noisy side of your circuit. And that's because you will then improve the EMI performance of the part. So this is very easily explained, as is if you have a multiple layer part, for instance, and your start of winding is right here under that yellow dot, well, the noise will be basically shielded by the second layer of winding of the part and will not go outside of the inductor. And same thing for single layer. Instead of connecting that, so single layer parts are typically built with one short side, then you do the windings, and then you go down straight with like a piece of straight wire. And that piece of straight wire is a little bit more susceptible to radiate noise around, so you want to connect that short end to the noise side to avoid this long end of wire, this long piece of wire to radiate the noise. So that's just a quick thing to look into. We have done a presentation for APEC on this topic, and you can go and look at it if you're interested to know more about it. So that's kind of what we have for this particular inductor design. Obviously, this is not everything, and the the main takeaway for this presentation is that to design a magnetic component, you always have to choose between three things, and you can only pick two of them. So either you pick a part that is very performant and that's very small, but then the cost is going to be high, or you pick a part that's going to be cheap and that the size is going to be small, but then the performance is going to be down. So you always have to choose between those three parameters and try to optimize around those and find the best compromise. But basically you never win, but sometimes you make better compromise than others. And I think for this particular design, we did a good job with EPC to optimize the part, because we were able to achieve very good efficiency, and I think Brian will actually tell us more about the overall board efficiency in just an instant.
Okay, thank you, Quentin. That was a lot of good information and a good explanation of all the factors and parameters that go into inductor design. Now, the next step that EPC decided to do was to actually build a board, bring everything all together. The board is actually available. It's a board part number EPC 9148. There's a link at the end of the presentation in case you'd like to look at the details. But here's a photo of it. You can see the inductor here, the thin inductor, the efficient high power inductor. And in the red box over here, the particular EGAN FETs. The larger one, the bluer one here, that's EPC 2053. That's a 100 volt rated FET. There's 3 of the 40 volt FETs, which are the one down here, the medium sized one. And there's also a very small one. This is only 0.9 by 0.9 millimeters, EPC 2038, in the gate drive circuit, in the boost circuit. So this is the board, and you can see as you here we go. You can see a side view also. You can see the height off the board is 4.1 millimeters. And there's the okay, so there's the height of the board. Okay, let's go on and look at some test measurements on this board. Design verification, validation. It's efficiency curve with a 48 volt input. Now there's 2 conditions of 2 different output voltages. The first is 20 volts. That was the original specification. The second in red, that's for 12 volts output, which is also a very popular output for the range of 48 volt input. You can see here how it reaches nearly 98% for a good part of the curve at output of 20 volts. And at 12 volts, it's actually very high also. Looks like above 96.5% for much of the efficiency curve. How about thermals? Let's look at the thermals, because after all, this is a small board. It's kind of pushed together. Here's a thermal image of the board. And this is taken under the condition of 48 volts input to 19 volts output and 12.5 amps, which was roughly 238 watts. The maximum temperature of the board is less than 65 degrees C. There's no heat sink. There's 800 LFM forced airflow. So that's good results. Let's look at a summary. Once again, to recap, the design goals were for ultra thin and very efficient. 2 very difficult goals to have, especially at higher power, such as this one, 238 watts. We looked at the various topologies. Flying capacitor, multi-level, synchronous buck converter turned out to be the best choice for this particular set of specifications. But the final result depends very heavily on the inductor, both for the size and for the efficiency and the proper operation. So high power thin inductor by Wurth is really key to this design. Looking at the result, the small size, not just the height, but also the XY direction is a nice small size. You have 98% efficiency. It uses standard off-the-shelf components, the maximum component height is 4.1 millimeters. If you'd like to look more into this design, here's a link to the homepage for this board, the EPC 9148 board. On this link, there are schematics, there's Gerber files, there's a bill of materials, and some other information on the board, as well as information on how to order it should you choose to do that. And thank you very much, and appreciate your time and attention. Thank you.
Okay, thank you very much for presenting today, Quentin and Brian. Now, at this point, if you do have any questions, feel free to ask them in the questions box, and we'll go ahead and get a few of those answered. Now, if we do run out of time, or if you think of a question a little bit later, feel free to reply to our follow-up email that is here for you at we-online.com. You will be seeing the video on demand, as well as a PDF of the slides within the next 24 to 48 hours. So you will be receiving the recorded presentation with the questions. Our first question here: do you have a design tool to select the magnetic inductor for ultra thin high power? I believe Quentin has the answer to this.
Yes, thank you, Amelia. Indeed, we do have magnetic inductor design tool. It's not really a design tool, it's more of a selection tool, where you can actually find out what part works best for your design. So you can actually go into this tool. It's a cloud-based tool. It's called Red Expert. Simulate your design. So whether you do a buck, a boost, or buck boost topology, and enter all your input and output parameters, your output current, your desired ripple current. And then based on this, the tool will kind of auto-select, create some filters to find the best part. But you can add on top of this whatever requirements you have. So if you're looking for an ultra thin part, then you can definitely set size requirements, and it will filter out the parts that don't fit. So this is the select off-the-shelf part. When it comes to designing purely a part, then you'll have to get in touch with us, and we're more than happy to help you achieve your design goals.
All right, thank you very much for that answer, Quentin. I think our next question is also for you. The question is the multiple gap design noisier than a center leg gap?
So I completely understand where this question is coming from, because you see the gap is now on the outside of the part, and now you think, well, now I have magnetic field leaking out, and that'll be true in theory. In practice, though, we do not really observe significant changes in EMI behavior based on this design change. There is really minimum impact as opposed to other factors that influence the EMI of the inductor, like the PCB placement, watching for coupling with other components or traces around the layout, the material. All of this matters a lot more than just having this gap being a little bit different. So I would not be concerned if you're having failing an EMI test by 1 or 2 dBs, and maybe doing this or changing this would fix it. But I think there is a lot of other things to do first before this. Yeah.
Thank you. Our next question: what frequency is the EPC design operating? Brian, can you answer that for us?
Yeah, the switching frequency overall is 400 kilohertz, but the inductor actually sees twice that. So 800 kilohertz is what the inductor sees, but the transistors each only see 400 kilohertz.
Thank you, Brian. Our next question: would the efficiency be increased if Litz wire was used instead? I believe that goes to Quentin.
Yes, so it's an interesting question. I would be very interested to see. I don't think, though, because Litz wire has its own inconvenience. And one of the major inconveniences, as soon as you increase the frequency a little bit above 200, 300 kilohertz, then you have a lot of parasitic capacitance happening between the windings and between the strand of each wire. So I do not believe that the efficiency would be increased. I think we would create a lot of heat in the windings because of this. But it would be still interesting to test. So yeah, maybe some ideas for future testing. Yes, thank you.
Our next question here seems to be a Wurth Elektronik question, kind of our specialty. Do you have low profile, thin transformers design for AC to DC converters?
Well, that's a interesting question. I don't know exactly what you mean by thin transformers. If you mean planar, Wurth Elektronik is not doing planar transformers. However, we have a whole range of custom transformers that we do here in USA, in our headquarters in Watertown. So I would definitely suggest you to be in touch with your local Wurth representative, or just get in touch with us, tell us what you need, and we'll be happy to work with you to try to achieve your design goals.
Thank you, Quentin. Yes, if you do have any custom transformer needs, then we will make sure that we set you up with our engineers and our staff to get you all set up. Our next question, do you have EMI results for this particular EPC board? Brian, can you answer that?
Yeah, I think I can. I'm not sure we really do have EMI results. If anybody knows differently, please let me know. One thing we did notice, we do have waveforms on the web as part of the test report, as part of a quick start guide that shows the waveform switching without ringing. One thing that helps is having no reverse recovery charge, which can sometimes cause ringing. So no, I don't think we have EMI results for this board, unless somebody knows differently, but we do expect good results at the high frequencies based on the lack of ringing.
Excellent, thank you. We do have a few more questions rolling in. Again, if you have any questions, our presenters are on hand to answer them. Simply message us in the questions box and we will get to them. Our next question, I think we're headed back to Quentin on this one, is material data available for your inductors to select optimum inductor material for a selected frequency?
Very good question. Unfortunately, no. The reason is because this is very strategic information. As I was explaining in the presentation, this is really information that is hard to get. And the information that we create for ourselves is not the same one that probably our competitors or car manufacturers create for themselves. So it really depends on how you measure it and what information you're looking for. And yes, this is very critical, and we're not sharing this information. However, what we do, I'm going to bring up again our Red Expert tool, is give you estimate DC and AC losses for our off-the-shelf part. So using Red Expert, you can actually estimate the losses, DC and AC losses of each part. And this is a very accurate model because it's based on actual real-life measurements. So yeah, to answer your question, no, we do not provide post-material data. But we give everyone the possibility to estimate the losses of our parts using our Red Expert tool.
Thank you, Quentin. Our next couple of questions look to be for our efficient power conversion field applications engineer, Mr. Brian Miller. Our next question is, this is more from an EMC perspective. I believe it is relating back to the EMI results for the particular EPC board. So this is more from an EMC perspective. Does operating at 1 megahertz interfere with AM band frequency?
Yes, it certainly can. It really depends on the situation, but yeah, especially like in automotive and some other applications, operating outside the AM radio band is really desired. This particular board, again, operates 400 kilohertz switching frequency, which is below, but the effective frequency on the inductor is 800 kilohertz. So there's two things you could do if you really don't want to be in that band. One is lower the switching frequency, which yes, would increase the inductor size and inductor value, so forth. But you could avoid the AM radio band and probably increase the efficiency by even more. Another option is to go above 2 megahertz to avoid it on the top end. That's something that silicon MOSFETs have trouble with, but GaN FETs can actually do that. Yes, there might be some sacrifice in efficiency. Actually, there will be. but it can be done practically to go, again, above the AM radio frequency.
Thank you, Brian. Our next question, what benefit is the EPC GaN offering at such low voltages? What is the expected improvement compared to silicone MOSFETs under these design specs?
Yeah, that's a very good question, because I think what the questioner is asking that, as the voltage goes down, the difference between the silicon MOSFETs and the GaN, it does decrease a little bit. But there are still some benefits that are pretty key and really help with the GaN FETs, even at a lower voltage like a 40-volt FET. One of those is no reverse recovery, so you still have that. So you could still have very low dead time at as you switch. So it's high frequencies. As in the previous questioner asked, what if you operate above the AM radio band? Well, yes, you can help that by having lower dead time. There still is faster switching. And so, yeah, I don't have quite the same extreme benefit difference, but yes, there are some areas that still make it very attractive.
Excellent. Our next question here, we only have a few more and then we'll be wrapping up. Does using a heat sink with conducted cooling affect performance? Brian?
Yes, it should help. Using a heat sink with conducted cooling to keep the FETs cooler, that will reduce the on resistance as the temperatures, you keep that down. I think that's what the questioner is asking, versus leaving the FETs to operate at a high junction temperature. Yeah, the cooling can be done sometimes through the board using a heat sink or a heat spreader. This particular board uses the heat spreader, but a heat sink can be put on top of the heat spreader, or there's various ways of doing the thermals. And we at EPC are about to release on the web a thermal design tool to answer these types of questions more thoroughly. Heat sink versus conducted through the board versus a heat spreader.
That is excellent news. Our next question here is for Quentin. Isn't there two requirements, conducted and radiated EMI?
Yes, absolutely. This is completely right. The slide in the presentation is referring to the emitted noise, but you're right, there is a conducted and emitted noise to consider. In the case of this specific design and working with EPC, we knew that they have already a lot of experience with EMI mitigation techniques, and they are already extremely good at designing the layout properly to mitigate those conducted emissions. So I only brought this topic up with them because this was something new that we recently started to work a lot more on, the inductor orientation. So that was the new topic to talk about. However, if you were to qualify any design for EMC regulations, then yes, you'd have to pass conducted, radiated, and even more actually test to pass the EMC regulations. Yes.
Thank you very much for answering that question, Quentin. And our final question here is, could you share the link to the APEC presentations referenced in one of the slides? And we absolutely will share those links. You can actually find them in the follow-up email, again, that will be sent out within the next 24 to 48 hours following today's presentation. And with that, we are going to go ahead and wrap up today's Wurth Electronic Power webinar with efficient power conversion. Thank you, Brian and Quentin, for presenting today. And thank you, everyone, for joining us for our final presentation of 2021. Don't worry, we are going to return bigger and better than ever in 2022. I believe that we are starting to schedule out our online presentations beginning in January. So make sure you are looking on social media, in your email, and on our website at we-online.com. for all of our upcoming webinars. And don't forget, you can also listen to our new podcast. It's the Wurth Electronic WhatsApp Radio Podcast, where each week we are bringing everything new to technology into an audio format. We have our webinars and application notes. Last week was all about solving EMI on the PCB level. Very popular webinar presented by Laurent Focal. You can hear that on the Wurth Electronic WhatsApp podcast. And this week it's all about horticulture LEDs. You can listen to that podcast as it launches Thursday at 12 p.m. Central. Until next time, I'm Amelia Thompson. Thank you for joining us for the Wurth Electronic webinar. We'll see you later.